아, 오늘 좀 늦게 퇴근하고 한강만 보고 자려고 라면을 끓여왔습니다. 그래서 컴퓨팅 사고 저번에 바이너리까지 봤는데 일단 이어폰을 껴야겠다. 헤드셋을 끼고 오디오 아웃풋을 헤드폰으로 보내고 들어가기 전에 라면을 한 젓갈 먹어야지. 파김치 올려서 한 젓갈.
How then does a computer allow you to send text messages and emails and compose documents and so forth? We need to all agree how we're going to go about representing characters or letters of an alphabet, be it English or something else, instead. And any intuition for how, if a computer only has millions or billions of switches that can be turned on and off, thereby representing numbers, we could possibly go about representing something other than numbers, like the letter A. Say again? By a digit. So we maybe just need to agree as a group, you know what, let's all agree that the letter A, in the context of a word processing program or a text message or email, just needs to be represented by a number. And we all need to agree what that number is. So maybe super simply, let's just say A is 1, B is 2, C is 3, and so forth. And you could imagine then having a computer turn on lots of little transistors to represent A and B and C, so long as the software on that computer, as we'll see, knows that it's a word processing program and not, say, a calculator or something that's meant to use numbers alone. So it turns out that computers don't actually use the number 1 for A or 2 for B. It's a little bigger than that. The world decided decades ago that the capital letter A is going to be represented by the number 65. 65, which is to say, if you have a byte of information in the computer, and this is the ones place, 2s, 4, 8, 16, 32, 64, if a computer were to store the capital letter A using 8 bits or switches, it would just turn on those two, the 64's place and the ones place. And so when you have actually received a message in a text message or an email with the capital letter A, you have just received a pattern of zeros and ones somehow wirelessly or via wires representing that pattern. Specifically, this pattern here, if we draw it not as light bulbs, but as zeros and ones. So it turns out there are certainly more numbers than just A's and B's and C's. We have the whole alphabet plus punctuation thanks to a system called ASCII, the American Standard Code for Information Interchange, which is just a fancy way of saying that there is a well-defined map that humans around the world agreed on years ago that looks a little something like this. So A is 65, and I is 73, and dot, dot, dot to both ends. So that is to say, if you were to receive a message from a computer or from a friend saying 72, 73, 33, or the pattern of zeros and ones representing those digits, what message did you perhaps just receive? 72, 73, 33. Yeah, so hi. So quite literally, if you were to text a friend hi, they would receive a message that's essentially a pattern of zeros and ones, 72, 73, then something. It's actually not obvious from the chart what they are, but it turns out
Period.
33 was the number humans gave years ago to represent an exclamation point instead. So any of the other punctuation symbols you might see on your keyboard
mark.
similarly have numbers that a computer would use, that all of us agreed on years ago, to represent that value. But of course, this is a very American-centric at the moment, and indeed, the acronym ASCII has American in it, and so it was biased early on to American English, for instance. But there's so many more characters in the world, of course, such as accented characters and other languages altogether. And frankly, there's also these things these days, which even though they look like pictures, you access them via your keyboard because they are indeed just symbols in an alphabet. There are zeros and ones, patterns of zeros and ones that represent those characters as well. That's what's known as Unicode, and that's like a superset of ASCII, because ASCII way back when used only 8 bits, which is not terribly many to represent characters. Unicode uses 8 or 16 or 24 or even 32, which means we have way many more possible patterns of zeros and ones with which to represent things like this. So this is face with tears of joy. As of 2019, it is the most popular emoji sent on iOS devices at least. Does anyone want to hazard a guess as to what the decimal number is that represents a face with tears of joy?
3024.
Not 65. It's not 72, not 73. 800, higher than that. 10,000, higher than that. It's 128,514. That's how many emojis await us down the road, because the numbers are now getting this big, or equivalently, this pattern of zeros and ones. So at the risk of taking all of the fun out of ever sending someone an emoji, when you send that face with tears of joy, you're literally just somehow having your phone send a friend's phone this pattern of zeros and ones, and Android or iOS are presenting it as that yellow picture. But that yellow picture, of course, itself is an image, and it's composed of lots of little dots. And odds are, coming into this class, you're generally familiar with using images, certainly, and seeing the little dots that compose an image, especially if they're of low quality. You can really see those dots. And so in a face like the emoji, we have lots of yellow dots. How does the computer represent each of those dots? Well, according to a system called RGB, red, green, blue. So again, decades ago, people in a room decided, you know what? To represent colors, we still have to use just zeros and ones, little switches mechanically, but let's just all agree what numbers represent what colors. So we just need another system for
represent
that.
what
Now,
colors?
it turns out that RGB essentially composes any color of the rainbow by mixing together some red, some green, some blue. And by combining those colors one on top of the other, you can get any color of the rainbow you want. So this is to say, to store any dot on the screen, one pixel, so to speak, in an image that you might take as a photo or send to a friend, you are actually storing 3 values. 1, 2, 3. 3 numbers, really.
So
but of course, at the end of the day, are zeros and ones. Those 3 numbers just tell the computer how much red, how much green, and how much blue to use to represent some dot on a screen. So suppose that, coincidentally, a computer were storing the pattern 72, 73, 33, albeit with zeros and ones, light bulbs, back to back to back like this. Well, in the context of Photoshop or a browser or Apple Photos or the like, in the context of a graphical program, your computer is going to interpret this same pattern of digits and in turn bits, not as high, exclamation point, but as some amount of red, some amount of green, some amount of blue. And it turns out if you combine this much red, 72, this much green, 73, followed by this much blue, 33, what you get when you combine all 3 of those is that shade of yellow. So for every single dot in that emoji, that face with tears of joy, every dot in this image, and we can see it if we really zoom in, is stored using 3 values, some amount of red, some amount of green, some amount of blue, that we combined give you yellow or black or gray or anything else, depending on how you encode those values. Meanwhile, images or videos, things like this that you might see on the internet these days in the form of memes or anything else, are actually just images, but they're multiple images in the same file. If you've ever seen what's called an animated GIF, which this happens to be, that happens to be looping, all our human eyes are seeing is one image after another, after another, after another, really quickly, creating the illusion, therefore, of movement. But this cat is not actually moving. These are like 5 or 10 photographs of a cat in different positions, just being looped endlessly. And that, too, is all a video is. A video is just a sequence of images flying past your eyes so quickly we humans perceive it as actual movement. And so that's like almost everything we use to represent information today in our computers, right? We have zeros and ones from which we get binary, to which we then get decimal digits, but we can use those digits to represent, say, characters on the screen or colors on the screen, and in turn now even the more interactive. Now what about something like music in a computer? Another type of information you might want to represent. Well, if we had like a piano on the stage here, we could quantize the notes you're playing using just numbers as well, right? What note you're playing, maybe it's A, B, C, D, E, F, or G, or some variant thereof. Maybe how long you hold the key down for, and if you hit it really hard, maybe how loud it is. So you could imagine using 3 values, the note, the duration, and the volume, just to represent something like a piano song. Might be one encoding of a song, and I might use different values if I want to play it even louder and longer, and so forth. Which is to say that at the end of the day, no matter what media we use to represent information, it all reduces to zeros and ones.
I need one more lecture. Actually, one more part of lecture. 오케이. 바로 문자를 숫자로 표현할 수 있도록 정해진 약속이 있습니다. 그중 하나는 설명 미국 정보 교환 표준부 ASCII 코드입니다. American Standard Code for Information Interchange. We have numbers for the colors, which is a promise, right? But I think also the colors should be organized by on promised order. We write 72. Let's say 72 is red, but my red and your red can be different, so I thought there should be an, how can I say, compromisation or promise of a color, just like the numbers and the ASCII code or the Unicode. I think so. Should I? Yes, beauty in binary. Well, I just understood. Anybody? Other people try to do it. CS 50, 50. 50 just. I thought 5 is different. 0 is also a different digit, so. I thought 50 can be split 5 and 0. That's interesting. Algorithm. We talk about the computer, how the computer express the color or text, letter with binary code, just like by the binary digit. So let's see what comes after.
So once we have the ability to represent inputs, be it numbers or letters or colors or videos, now we can talk about outputs. So how do we get from inputs to outputs? That's what's inside this so-called black box. And this is where computer science comes in. An algorithm. Anyone know what this term is? What's an algorithm? You sort of read about it all the time these days, especially in the context of self-driving cars and Siri and Alexa and so forth. Yeah. A set way to do something. Yeah, and in the context of problem solving, an algorithm is just step-by-step instructions for solving some problem. So what might an algorithm be for a problem that we might want to solve? Well, consider this. This is an old school problem where you might have lots and lots of names and lots of numbers, and those names are hopefully sorted alphabetically from A through Z in a book like this. And even though most of us don't really reach for this technology anymore, consider that it's really the same as your iPhone or Android phone or other device, which has all of your contacts top to bottom, and you can scroll through them from A to Z, or you can search for them by typing into the little autocomplete box. How is even your phone solving this problem? Well, let's consider a simple approach. I'm going to look at the first page and look for someone on the phone book. Suppose that person's name is Mike Smith, last name starting with S. Let me go ahead and look down. He's not here. Let me turn the page. Let me turn the page. Let me turn the page. This is an algorithm. It's a step-by-step process for solving a problem, finding Mike Smith. Is this algorithm correct, would you say?
Algorithm is a step-by-step process to solve a problem.
Yeah, I mean, it's pretty slow. It's pretty stupid in that it's going to take, my God, forever, like hundreds of page turns to find Mike Smith. But if he's there, I will find him according to this step-by-step approach. What if I speed things up a bit just because it's tedious otherwise? So I do 2, 4, 6, 8, 10, 12, 14, 16, and so forth. Is that algorithm faster? Absolutely. Literally twice as fast. Is it correct? No, why? Yeah, we might skip them. I might get unlucky, and eventually I might get to like the S's, but darn it if Mike wasn't in between two pages as I turn them at once. So it's not a fatal flaw. That algorithm I could fix by just saying, if you hit the T section, or maybe SN instead of SM, just back up one or so pages just to fix that bug or mistake, so to speak. But it at least is twice as fast. But if this phone book has like 1,000-something pages, it's still going to take me maybe like 500 pairwise turns just to find Mike Smith. That's a while just to look someone up. But most of us, if you've used this technology, instead did what back in the day? Go like roughly to the middle, right? If there aren't little letters on the side of which to cheat. So go roughly into the middle. I'm in the M section. Now the M's, of course, mean that Mike is not this way, which would be the A's. He's probably this way toward the Z's because S, of course, is between the M and the Z. So at this point, I can literally tear the problem in half, throw half of the problem away very dramatically and unnecessarily, making the point that we've now gone from 1,000 some odd pages to what, 500. And I can do it again. I went a little too far. I'm now in the T section, so I can tear the problem in half again, throw that half away, and now I'm down to from 1,000 to 500 to 250 pages only after just 2 steps in this step-by-step process. And if I repeat this again and again and again, hopefully I'll be left ultimately with, say, just one page on which Mike Smith either is or is not, and I can call him or quit. So that algorithm would get me to the solution so much faster, and we can appreciate this even if we just look at some of the numbers ultimately as follows. So if I start with, say, 1,024 pages total in the phone book, and I'm looking for Mike Smith, and I divide and conquer this problem, splitting the problem in half and in half and in half, I go to 512, I go to 256, 128, 64, 32, 16, 8, 4, 2, and 1. After just 10 steps, I have found Mike Smith's page. By contrast, that first algorithm, where I just did one page at a time, how many steps maybe might it have taken me to find Mike Smith? Yeah, like 700, 800, roughly where the S's might be. So in the worst case, 1,000 pages if I look through the whole thing. The second algorithm, maybe 500 pages because I'm going twice at a time. But my God, 10 steps with this algorithm here. And odds are that would be the algorithm most of us in this room would reach for by default, which is to say that a lot of problem solving really, as we'll find, is just about harnessing your existing intuition and comfort with ideas that now you just need to translate in such a way that machines and other humans can understand. So how might we just think about how much better that algorithm is? Well, consider this first line here. On this y-axis or vertical axis, let me describe this as the problem. And on the horizontal or x-axis, the size of the problem. So the number of pages in the phone book would get bigger as you go to the right. And the number of seconds or page turns required would go up along the y-axis here. So that first algorithm, depicted here in red, suggests like a one-to-one relationship between the number of pages in the book and the number of seconds to find someone. So you have this straight line, a slope of 1 over 1, if you will. And so if we consider the second algorithm is also going to be a straight line, but that straight line is going to be lower on the graph. Why? Because for any size problem, it's going to take me half as much time to search that phone book, because of course I'm going 2 pages at a time. So if we see this, for instance, if this dashed line represents some number of pages in the phone book, maybe 1024, well, you can see that it might take this many seconds or page turns to actually find Mike Smith with that second algorithm. But in the first algorithm, that same number of pages would take way more time to solve, literally twice as much time in this case. Well, what about the third algorithm? Well, even if your memory of what a logarithm is a little hazy, it just describes a fundamentally different shape. The green line describes that third and final algorithm, whereby you divided the problem not 1 page at a time or 2 pages at a time, but 50%. Again and again and again. You halved it again, again, and again. And notice that as the number of pages in the phone book gets really large, you barely make an impact on how much time it takes to solve that problem. For instance, if Cambridge and Alston, 2 towns here in Massachusetts, merge next year and their phone books become one phone book that's twice as big, so not 1,000 pages each, but 2,000 pages total, how many more steps might it take us to find Mike Smith in next year's phone book if it's got 2,000 pages instead of 1,000? Just one more step. But the first 2 algorithms, that's another 1,000 steps maybe, or another 500. These are fundamentally big differences in efficiency, so to speak. So let's translate this idea, this intuition, into the first example of code. This is pseudocode, and there's no one formal definition of this. Pseudocode is like code-like syntax that you write in English or your own spoken language that represents your ideas, but in a succinct way. And so I might propose that this algorithm for finding Mike Smith might be written in pseudocode, English-like syntax as follows. Step 1, pick up phone book, which was indeed the first thing I did. Step 2, open to the middle of phone book, which is the next thing I did. Step 3 might be look at the page to see if someone's there. And if Smith is on that page, what do I want to do? Well, my code's going to look a little different now, and I'm going to deliberately indent to make clear that there's a dependency of some sort. I'm going to go ahead in step 5 and call Mike only if line 4 is true, that he's on the page. Else, if Smith is earlier in the book, to the left, so to speak, I'm going to go ahead and open to the middle of the left half of the book. And then what am I probably going to want to do next? So yeah, this ultimately, how do I do this again and again? Well, I already have some code, if you will, on line 3 that does that. Look at page and then make a decision to go left or go right. So I'll just say go back to line 3 after going to the middle of the left half of the book if Smith is indeed earlier in the book. The other scenario, of course, is the opposite. So if Smith is later in book, let's open to the middle of the right half of the book, and then let's go to line 3. Else, there's a fourth possible scenario or case. What else might happen in this algorithm? He's not there, and so I probably want to anticipate that and just say quit, if indeed he's not on the page, to the left of the page, or to the right of the page. So there is one way of expressing this pseudocode, albeit now in just this English-like syntax. But in this syntax alone, there's some commonalities, some features we're going to see over the next several weeks, not only in pseudocode, but in a language called Scratch, a language called C, a language called Python, and more. There are certain constructs in programming, procedural programming, so to speak, that are going to be common among all of these languages. Highlighted in yellow here are what henceforth today and onward we're just going to call functions. These are verbs or actions that just tell the computer, or in this case the human, what to do. So those are functions. Now highlighted in yellow instead are what we're going to call conditions. These are branches, sort of forks in the road. So you can either do this, or you can do that, or maybe this other thing as well. But to make those decisions, you have to ask yourself a question. And those questions in computer science are called Boolean expressions, after a mathematician named Boole. And a Boolean expression, highlighted now in yellow, are just questions that have yes or no answers, or if you will, true or false answers, or heck, now that we know binary, 1 or 0 answers. So even in code, we see a hint of why 1s and 0s are helpful. Lastly, there's this thing here. Go back to line 3. We've used it in 2 places. That refers to something we'll call a loop. It's a cycle that does something again and again. So beyond those 4 ideas, functions, conditions, Boolean expressions, and loops, we're about to see a bunch of others as well. Variables, reminiscent of what you might recall from algebra, but more powerful now in this context of programming, something called threads and events. And we're going to do this by way of an actual programming language. But it's not yet going to be this one. Indeed, just a week from now, will you actually understand what this means? Odds are 2/3 of you have no idea what this actually is, and that's OK. But it's a program written in a language called C, more on that next time, that quite simply says hello to the world.
That's interesting. The point is this lecture, there is a like grammar or rules how to tell the computer what to do and how to do it, right? I think so. Is there any punchline? Like punchline in this lecture? Algorithm is a step-by-step process to solve a problem. So depending on the algorithm, the problem solving can require a small amount of time or way large amount of time, much longer time, right? And so how it depends on how to design the steps to solve a problem. Okay. I was trying to see just one lecture, but I already watched 2. And it's almost 1 a.m. and I have to go to work tomorrow. That means I should stop here and leaving some portion to do it. It helps me to do it again tomorrow. This kind of approach is not 열심히, but it can be 근근히, also 꾸준히. So I will stop here, and before I stop watching the lecture, I want to read these descriptions, explanations. 알고리즘. 전 강의에서 숫자, 글자, 색깔 등을 컴퓨터가 이해할 수 있는 이진법으로 표현한 것을 배웠습니다. 이것은 입력에 해당하는 것입니다. input. 이제 출력에 대해 이야기해 볼까요? 그럼 어떻게 입력에서 출력을 얻을 수 있을까요? 컴퓨팅은 입력을 받아 그 입력을 처리한 후 출력하는 과정입니다. 다시, 컴퓨팅은 입력을 받아 그 입력을 처리한 후 출력하는 과정입니다. 알고리즘은 입력에서 받은 자료를 출력 형태로 만드는 처리 과정을 뜻합니다. 즉, 알고리즘이란 입력값을 출력값의 형태로 바꾸기 위해 어떤 명령들이 수행되어야 하는지에 대한 규칙들의 순서적 나열입니다. So it means step-by-step process. 어려운 용어가 나오지만 억지로 이해하기보다는 우선 넘어가시고 아래 예시를 이해해 주세요. Yes, the Korean explanation was way more. It can be way more difficult to understand. If I just saw the English lecture and the professor, what was his name? Magnon? Naren? Let's check his name again.
8. This is CS.
Computer thinking, scratch. Let's
This is
hear his name. David Malan. David Jim. He maybe introduced himself at the beginning of the lecture. Maybe. I hope.
This is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Arts of Programming. My name is David Malin, and
David Malan. Thank you for introducing yourself. And his name David Malan. Malan told me, I was told. No, I just saw his lecture and I heard what he said. And compared to this description, his explanation is way easier than this explanation. Also there is 입력값, 출력값, 어떤 명령들이 수행되어야 하는지에 대한 규칙들의 순서적 나열입니다. Let me translate this into English. So algorithm is arrangement, consequent arrangement of rules about what kind of command should be executed to change input to output. So algorithm is a consequent arrangement of rules to process or to change the input to output. Let me try again. Algorithm is an consequent arrangement of rules about what kind of rules? The rules about what kind of command should be executed to change the input to output. He just said algorithm is a step-by-step process to solve a problem. That's it. That's what he said. 이러한 일련의 순서적 규칙들을 어떻게 나열하는지에 따라 알고리즘의 종류가 달라집니다. 같은 출력값이라도 알고리즘에 따라 출력을 하기까지의 시간이 다를 수 있습니다. 정확성도 중요하지만 효율성도 중요합니다. 정확하고 효율적인 알고리즘. 의사코드, pseudocode is 의사코드 in Korean. 의사코드는 필요한 행동이나 조건을 잘 설정하여 컴퓨터가 수행해야 하는 일을 절차적으로 파악할 수 있게 도와줍니다. pseudocode set up the required behavior or conditions so that the computer understand what should be done. consequently. Conditions, admit conditions, and this Boolean, both yes or no question. So it translated it translated to 1 or 0. So true or false. What's an algorithm? David J. Mellon.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step.
Here the line.
What's an algorithm?
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem step by step.
Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language.
Resembling programming language, pseudocode.
Let n equal 0.
Let n equal 0.
Set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm does twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all, since there aren't any pairs of people in the room, and so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2. But then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1.
To solve this particular problem, we've introduced in line 4
But she
a
does not
condition,
look happy.
otherwise known as a branch, that only
this
executes
idiot
if there's
looks
one
happy
person we
with
could
this
not
guy.
pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s, but beyond that it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to
Set
solve
of
problems.
instruction
These were just
which
3.
is designed to
What
solve
problem would
problem.
you solve with an algorithm?
His explanation so clear and easy to understand. And I love it. He talked on. He have talked about the algorithm intended. Great. Too loud.
Every day, the sands of the Sahara Desert reach temperatures up to 80 degrees Celsius.
Great. That's funny. Okay, let's go back to the computer science, and I just hit the complete this lecture and just take a look what's coming. Oh, this scratch and fundamental or basic. Before getting to it, algorithm, to make an algorithm, you can use a variety of programming languages. The easy way, one of the easy way is Scratch, some graphic programming, just like Scratch, is it can be best way. Okay. This looks like just elementary school kids game. Oh, he talked about the language C. Crazy. The C is where I give up the learning programming. So I'm happy to see it again here. Okay. Memory. And the source structure. Data structure. Right. Crazy. I like this course. That's why I saw this lecture at this midnight. Okay, thank you everyone. I'm done today. I'm going to bed after brushing my teeth. See you